Hi there, Dr. P here, and in this lecture video we're going to take a look at the quantum mechanical model of the atom. And this is a model of the atom that was developed to compensate for deficiencies in the Bohr model. Now we saw last time that the Bohr model of atom works great for hydrogen, but it turns out it doesn't work so good for other elements. So what was developed was, this is by several scientists, Erwin Schrödinger, scientist by the name of de Broglie, and then Werner Heisenberg, and it's also known as wave mechanics. And so it's based on the properties of electrons, that they have both particle and wave nature. So electron has wave properties. That is, it's got a wavelength, frequency, etc. And so in quantum mechanics, the wave properties are emphasized. So we can think of an electron in the atom as being a sort of standing wave, if you will. What's a standing wave? Well, something like a guitar string would be a standing wave. So E minus as standing wave. So just, as an example, we could have, we've got like a half a wavelength there. We've got a wavelength like that. We've got like that, etc. Okay, and it goes up and down, of course, because it is vibrating. The same sort of thing. So these standing waves are stationary. They don't propagate in any direction. And then in atoms, only certain waves can fit into a quote-unquote orbit. Only certain waves fit into orbits. Okay, so if we had an atom, let's say, so here's our atom, and then here's our wave here. 3, 4, 5. So here we have n equals 5. We have some whole number integer of wavelengths. Okay, so this is a whole or integer number, because integers are whole numbers, duh. Integer number of wavelengths. That is integer number of peaks. I'm referring to those as wavelengths. And we could compare this to something like that maybe has 1, 2, 3, and a third. And that simply will not work. That won't fit. Okay? Now, does this work? Well, yes, it does. And it actually takes on quite a mathematical turn, and what we get is the Schrödinger equation. And I'm going to show it to you, but you're not going to need to do any math with it, which is a good thing. Believe me, that's a more advanced physical chemistry course. So the Schrödinger equation is h hat psi equals E psi. Now what are the parts here? H hat is an operator. which is a bunch of math, a bunch of mathematical calculations, operations. E is the total energy of the atom. And this includes the potential energy of the proton-electron attraction and the kinetic energy of the electron. And then psi is the wave function. And what's a wave function? Well, it's a mathematical function of where the electron is in space. So we'll say where electron is in space. Now this might look like it's a trivial equation and you look at it and say, oh, this means that h hat equals E. Well, that's not the case. This is not h hat times psi, it's h hat operating on psi. Basically what you do is you have a wave function, some description of where the electron is in space, do a bunch of funky math on it, and you get the energy of the atom, which is what we're looking at. Now, it turns out that there are many solutions to the Schrödinger equation, and each solution is a wave function that's characterized by a particular value of E. So let's just say here, many possible solutions, psi and E values specific, and this one of these specific solutions, so a specific wave function, is called an orbital. Okay, and that is similar to the word orbit that Bohr was using and that de Broglie was using up here, but orbitals are not the same things as orbits. That's something important to know. Okay, so let's take a little bit closer look here at what's going on. So some important things to note. Again, the orbit does not equal the, an orbital does not equal an orbit. So let's just look at hydrogen. So we'll look at the wave function corresponding to the lowest energy for the hydrogen atom. So we'll look at the ground state of hydrogen. And this is known as the 1s orbital. And it's a spherical orbital. And we'll talk in next lecture about the shapes of orbitals. Remember, orbital does not equal orbit, even though they sound similar. And then we have the question of how is the electron moving? Where is it? And the answer is we don't know. We don't know exactly. Okay, and that's due to what's known as the uncertainty principle. Also called the Heisenberg uncertainty principle. And what Heisenberg discovered was that there's a fundamental physical limitation to the precision with which we can measure both the position and momentum of a particle at a given time. So mathematically, we can express it as delta x times delta mv is greater than or equal to h over 4 pi. Okay, and delta x is our uncertainty in position. Delta mv is our uncertainty in momentum. And then h, of course, is the Planck constant. And pi is 3.14159, etc. So it's interesting to try this for an electron and for a baseball, say a fastball, and maybe I'll have you do that in the group activity. All right, so supposedly Heisenberg was quoted as saying, "For now we know that we shall never know." On a practical everyday terms, like for a baseball or me waving this pen around, we don't need to worry about the uncertainty principle. But it is important for really, really small things like electrons. Okay, and I want to talk about absolute size. And you think about things being large or small, and my pen is small compared to an elephant, but it's large compared to an ant. Now there is an absolute size scale, and we can say that something is small when the minimum uncertainty with which we can measure its position or momentum is approximately the same size as the thing itself. Okay, and this is the case for things like electrons and actually photons, small, really, really small particles, and that's why they also behave like waves. We have this certain inherent uncertainty that we don't know exactly where and exactly how fast something is moving, because that's the velocity part of momentum. All right. Now, what does this mean for what we're doing here? I mean, I've been talking about quantum mechanics. So, what does this mean for an atom? Well, given the uncertainty principle, we can't know the exact motion of the electron in an atom. Thus, we don't have orbits, but we do have orbitals. Okay, so orbits are out. Orbitals are in. Now, what is an orbital? Well, if we look at a wave function, maybe I'll go to a new page here. If we look at a wave function and take the square of the wave function, so our wave function is some function in our spatial coordinates, x, y, z, and we square that, we'll get some probability, which we'll just call n. And it's the probability of finding the electron near a particular point in space. So probability of electron, probably of finding electron near particular point in space. And so for the 1s orbital, if we have our probability and then we have our distance from the nucleus on the x-axis, we see that what we get is a decreasing probability. And so we have essentially something spherical where we've got our nucleus in the middle, and then we have essentially a cloud that gets more and more diffuse the further out we go. And sometimes this is called a probability density or just electron density. And so ultimately there is a small but finite probability of finding an electron, on the other side of the room, but it's so tiny that we essentially ignore it. So how big are these orbitals? For a hydrogen 1s orbital, the maximum probability is at r equals, or maximum radial probability is at r equals 5.29 times 10 to the minus 2 nanometers. Not going to write that down, but interestingly, this is the radius of the innermost orbit in the Bohr model. And so our size definition, so we'll say atom size, no, we'll say orbital size. %90 of total electron probability. So if we're looking at a 1s orbital, which is a sphere, the size of the 1s orbital is the sphere that encloses 90% of the total electron probability. So we can think of these orbitals as sort of two different things. One is the probability of finding an electron at any given point in time. And the other is where we have a 90% chance of finding the electron. That gives us our overall size. So an electron in an orbital is really a cloud of probability indicated by the orbital map. Now, this is all well and good, but how are we going to do chemistry with this? Well, that's where we have what are called quantum numbers. And quantum numbers come out of the different wave functions that satisfy the Schrödinger equation for the hydrogen atom. So there's a bunch of math involved, but the quantum numbers are integers that describe the math. So we pull out all the mathy math, and we're left with a bunch of whole numbers, with the exception of the electron spin quantum number, but we'll get to that later. Okay, so quantum numbers characterize different orbitals. All right. I think I'm going to push off quantum numbers, the discussion, for the next lecture, because that segues into what they look like, and I have some models here to show you guys. So we'll start off next time talking about quantum numbers, but take home from this lecture, we have a more accurate model of the atom than the Bohr model, and it's the quantum mechanical model of the atom. It actually works perfectly for hydrogen, works really well for other atoms, but not exactly. And so, we have to make some approximations or assumptions. But you can use quantum mechanics on molecules as well and come up with really good results as well. Compare that to the Bohr model, where it only works for hydrogen and actually fails miserably for explaining properties of other atoms. All right. Well, until next time, stay safe out there. Bye now.